Simple harmonic motion is known as the motion of a mass on a spring when it is subject to a linear elastic restoring force, also known as the spring constant, given by Hooke's law. By calculating the spring constant along with amplitude and frequency, the team is able to determine which of the three oscillators should be recommended. The team has been hired by the lab administration to build and develop 3 different harmonic oscillator clocks with a certain mass hanging from a spring and oscillating with a constant amplitude and frequency. After analyzing the motion of each clock, the team was able to calculate frequency, period, and the spring constant for each trial.
So in the blue spring video, the blue spring had a spring constant of 30 Newton meters. Nathan calculated the mass to be put on there to get as close to a period of 1 second as possible, and the mass we used was 760 grams plus or minus 76 grams.
This slide shows all the graphs of position versus time, velocity versus time, and acceleration versus time for the blue spring with the force constant of 30 newtons per meter. And from the graphs, you can see that no matter whether it's the position, velocity, or acceleration, that all the periods are very close to 1 second time intervals. The only difference is that we started the video when it wasn't exactly on the right second. So the graphs are a little bit to the right or left of the exact 1 second or 2 second or 3 second, but all the graphs are very close to 1 second periods. In this video, we used a green spring. The green spring had a force constant of 50 newtons meters, and from Nathan's calculations, it was required for 1,260 grams to be attached to the spring to give us a period of 1 second, and this will give us also a frequency of 1 cycle per second.
This slide displays information for the green spring. The green spring had a spring constant of 50 Newton meters. In this slide, we show the position versus time, velocity versus time, and acceleration versus time graphs. Just as the blue spring information, the general period for each of the graphs you can see is close to 1 second time intervals. Obviously, there's going to be an error just because it wasn't started exactly at 1 second, so it's going to be shifted to the left or to the right based on when the period started. In this video, we used the red spring. The red spring had a spring constant of 25 Newton meters. We used Nathan's calculations to acquire that the mass needed for a period of 1 second is 633 grams plus or minus 63 grams. If the period is 1 second, the frequency should be 1 cycle per second.
This slide shows the graphs of the red spring. The graphs are the position, velocity, and acceleration versus time. And just like the blue and green springs, all of the troughs and crests have a 1 second time interval, which it gives a period of 1 second and a frequency of 1 cycle per second. And they're very close to 1 second intervals, and the differences could be caused from we may not have started or given an acceleration to the spring on an exact time second, or the camera could have tracked just a slight difference, but they're all very similar.
This slide shows the calculations that are required to find the mass on a specific spring for an oscillation with a period of 1 second. The givens we found from the red spring were 25 Newton meters plus or minus 10% uncertainty. The blue spring was 30 Newton meters, and the green spring had a spring constant of 50 Newton meters. The equation I used to find the corresponding mass to spring was T equals 2 pi square root mass over the spring constant K. Next, I solved for M, and M turned out to equal T over 2 pi squared times the spring constant. But that only gave the mass in kilograms, and in lab we were using grams. so I had to divide by 1,000 to convert kilograms to grams. To find the uncertainty for each mass, I had to use the uncertainty formulas for multiplying two numbers together with different uncertainties. The uncertainty of the time over 2 pi squared was only in order to find the uncertainty Q for each mass, I had to use the uncertainty formula for multiplying and dividing with uncertainties. The uncertainty for the term T over 2 pi squared has an uncertainty of 0 because the time we're looking for is 1 second, and 1 second does not have an uncertainty, plus the uncertainty of K, which was given as 10%. So 10% of the spring constant was the uncertainty used for the second term. In the third term, the uncertainty for the conversion factor of kilograms to grams is a 0 uncertainty, so that is also 0. But with a uncertainty of 10% for the spring constant, when it gets multiplied and divided, it grows significantly. And then in the equation, you multiply by the total answer, which is m, to give the uncertainty of 63 for the red mass spring, 76 for the mass of the blue spring, and 120 for the mass of the green spring.
After doing calculations and plots for each oscillator, the team recommends using the clock with the blue spring. The blue spring oscillator has the closest period of 1 second by looking at the graphs, and compared to other springs, it was also calculated to have the smallest uncertainty. Some potential improvements that could be made to the experiment would be starting the time the oscillator begins at 0 to be able to see the exact length of the period, measuring the weight hanging using a more precise instrument, and minimizing horizontal motion during oscillation.